Morning, everyone. Hope you are guys doing well. Today we have Mats. He has been with us for ages, I believe. He did bachelor and master at KU Leuven, doing PhD at KU Leuven. I just learned that he is on FWO project and been co-supervised by Leen and Stéphane Matisse from Paris. And Mats is going to talk about the AGB stars in binary systems. Not that, these systems as single stars, they weren't complicated enough. It's just that doing binaries is much more fun than doing single stars, I believe. Enjoy, and the floor is yours, Mats.
Thank you. Okay, hello everyone. Welcome to my seminar, indeed on the orbital evolution of AGB binary systems. So, what exactly am I working with? I'm working with stars, more particularly low and intermediate mass stars, like our Sun, that at some point in their life will evolve to a red giant phase, meaning a red giant branch, RGB, or asymptotic giant branch, AGB phase, AGB in this case. So these stars are enormous, huge in size, as well as extremely bright. And because of these properties, they will lose a significant amount of their mass through what we call a stellar wind, creating these beautiful structures around the star. And indeed, as Andrew said, these stars are luckily not alone. If you look at our Sun, we have a few planets, but these also aren't always planets. These can also be stars. And this is what we call a binary system. And when one of these stars is an AGB star, I call it an AGB binary system. And looking at binary systems, and more particularly their orbits, these orbits aren't always stable. These orbits aren't always the same. They will move, they will evolve. And the study of this evolution is what we call the orbital evolution, in this case of AGB binary systems. And why is this important? Why do we care about this? Well, first of all, for the fate of the companions. Looking at stars that orbit a star that will evolve to an AGB star, like for instance our Sun, for instance our Earth, will the Earth or other companions remain on such a stable orbit or move outwards and survive the violent AGB phase, or will they spiral in, plunge into the star, and start the common envelope phase? Other than that, if we look at orbital statistics from companions in a later evolutionary phase than the AGB phase, so we have stars orbiting post-AGB phase, post-AGB stars, and post-AGB, with that I don't only mean the post-AGB phase itself, but just stars that are in a later evolutionary phase than the AGB phase. We see a discrepancy between theory and observations. And this can be seen in the diagram here, beautifully made by Hans, where you have observations of such systems, the dots on the diagram, and you see the predicted theory in the blue background. And you can clearly see that there's a discrepancy between the two. And if you want to understand where this discrepancy comes from, what we can do is further investigate the orbital evolution and try to get as accurate as possible in our predictions. So, to look at orbital evolution, we first need to understand how does the star evolve. And to do that, I do stellar structure and evolution models with the stellar evolutionary code MESA. And here I show a Kippenhahn diagram for a one solar mass model. And which means that I show the regions where it's convective in orange and radiative in yellow. And here I show on the x-axis stellar age in a logarithmic scale, which means that we can see the pre-main sequence as well as the main sequence very well. But we don't really see the evolved phases. The evolved phases are the teeny tiny bit here. So you can plot it in a linear scale to see it a little bit better, where we now see mainly the main sequence, but also the RGB phase, where you get the helium shell burning and the radius starts to increase. But the further evolution we still don't really see. So you can try to plot it in yet another way, which I do now in computing or showing the stellar age until the stellar age where the star is cooled down to become a white dwarf. And when you do this, you have all the phases very nicely. You see the main sequence phase here, radius increases in the RGB, then you have the helium flash, the start of the horizontal branch. Then you have shell burning again in the AGB with an increase in radius where it loses its outer envelope, and then you're left with the post-AGB and then becomes a white dwarf. So now that we have our stellar evolution and our stellar structure, we can try to compute the orbital evolution. And if we want to compute the orbital evolution, what type of phenomenon do we need to take into account? Well, for that, we can look at another celestial body we have close to us, and that is the moon. And if we measure the distance from the Earth to the moon, we actually see that it increases by about 3 centimeters every year. And why does this happen? Where does this come from? Well, this is actually due to tides. You have tides, high tide and low tide, coming from the moon in the oceans, and the Earth is spinning faster than the moon is orbiting around us. So you have angular momentum from the spin of the Earth that is transferred to the orbit of the moon, increasing the orbital distance. This phenomenon also occurs inside stars. You have high tides and low tides inside stars that can couple angular momentum from the spin of the star to the orbit of the companion. But this isn't the only effect that we need to take into account. I said before that the evolved stars have mass loss, and this mass loss we need to take into account as well. You can imagine that if mass is lost from one of the bodies, the gravitational influence for both stars will change, and also the orbit will change. So let me go into detail for both phenomena. First of all, the equilibrium, or the tides. What I talked about, the tidal bulge and the movement of these tidal bulges, is what we call the equilibrium tide. But this isn't the only tidal effect that takes place. Because of this periodic motion of the tidal bulge, we also have a periodic movement. And a periodic movement can trigger waves and trigger pulsations. And these additional tides, or this can generate additional angular momentum and energy transfer, is what we call the dynamical tides. Now, waves need to be at specific frequencies, or specific frequencies can trigger different type of waves. So what waves or pulsations do we need to take into account for our evolved stars? To know that, we can look at, again, our internal structure of such stars, where here I show specific frequencies or important frequencies throughout, or for a snapshot throughout the AGB phase, where I show the Lamb frequency in orange, and above the Lamb frequency, pressure waves can be excited, and you have the Bruin-Feisler frequency in blue, below which gravity waves can be excited. And if you take an orbital period of about a year, then that means that you have a specific tidal frequency, which I show here in green, and that's the frequency where tides can generate waves. And you can see that there's no region inside the star where the green line is above the orange line, so no pressure waves will be excited by tides in the evolved phases, but there is a region where you have the green line below the blue line. So you can generate gravity waves, and this will happen exactly at the interface where the green line crosses the blue line, so at the interface between radiative and convective regions. So throughout stellar evolution, at this interface that moves, you have gravity waves that are launched from the interface inwards towards the center of the star. And this we need to take into account in the tidal dissipation as well. So we have equilibrium tide we need to take into account, and the dynamical tide of gravity waves. So if we have these phenomena, how can we compute how the orbit will actually change? Here I'll show a little bit of equations, but I've always chosen a circular orbit to simplify it a little bit. And now you can see that the change in semi-major axis can be related to what I call here kappa. And kappa is the love number, or in this case actually the imaginary part of the love number, but I'll come to that. What is a love number? A love number is the gravitational readjustment of a body divided by the gravitational perturbation due to the companion. So you have a gravitational perturbation, since you have an extended body, gravitational perturbation from the companion. This will influence the material. This will get a gravitational readjustment, and that's the love number, giving you the tidal bulge. But taking the imaginary part gives you actually how much dissipation can happen. How does this lag behind? Giving you how much angular momentum can be transferred from the spin to the semi-major axis and the other way around. For these love numbers, these imaginary part of the love numbers, can we calculate them from stellar evolutionary models? Well, yes, there's a few ways we can do this. You can either infer this from observations and try to get equations and plug them on top of stellar evolutionary models, or from first principles, you can try to compute them. And it's the second I do here. So I get stellar evolutionary parameters and try to compute this imaginary part of the love number. For the equilibrium tide, this is proportional to the equation I show here, where you have a proportionality to the tidal frequency. You have an integral over the entire body of the density, the viscosity, which gives you the friction. This viscosity is dependent on the radius, but also on the tidal frequency itself. Then you have the term d, which is proportional to the actual movement of the tidal bulge. And then you have an r squared coming from spherical geometry, and this integral you can compute. So for every snapshot throughout stellar evolution, you can compute how much will the equilibrium tide dissipate energy and angular momentum. You can do the same for the dynamical tide, but now it's different properties that you need to take into account. You have the tidal frequency, this time to the power 8/3. And you have properties dependent on the interface between the radiative and convective zones. So you need to take into account the density, the radius of this interface, also the change in Brun-Weisler frequency at this interface, and the tidal forcing, what is called F. What is this tidal forcing? It's a term related to how much the equilibrium tide can push at this interface to launch these waves. So both of these phenomena we can compute at every step of stellar evolution, and we can compute images that look like this. So here on the x-axis for both of them, I have stellar age, and the y-axis I have orbital period. On the right diagram, I also plot the critical period. What does this critical period mean? It's actually the period at which an assumption we make falls down. So I assume that waves don't interact with each other and no modes are created. And below these lines, we cannot assure that anymore. So we might need to take that effect into account as well. But above this line, modes will not be created, and we can trust this formalism. So what do we see? We see that there's difference both when you change the orbital period and when you change the stellar age. First orbital period, you see that when you increase the orbital period for the equilibrium tide, first the love number increases and then it decreases again. This is not only because of the linear dependence of the frequency, but also because of the dependence of the viscosity on the tidal period, or the tidal frequency, sorry. But also when you increase stellar age, you can see that here the love number increases. So when the radius increases, the love number increases. And here as well in the AGB phase. So in the AGB phase and the RGB phase, the equilibrium tides are important. Now for the dynamical tide, you have a different dependence. In terms of orbital period, because you have the tidal frequency to the power 8/3, it's a strong decrease. It's a strong decrease in terms of or when you increase the orbital period. So they're important when you have a low orbital period. It increases when you increase, or throughout the main sequence in the beginning of the RGB, but throughout the RGB, it actually decreases. It increases again when you go to the horizontal branch and decreases throughout the AGB. So during the evolved phases, it might not be the dynamical tide that is important, but still it's always good to include it. So as I said before, you can, or using both images, you can combine them to see what part of the parameter space what type of tide is important. And as I said, during the giant phases, it's going to be the equilibrium tide, which is in blue here. The blue is where the equilibrium tide dominates, and red is where the dynamical tide dominates. So for the evolved phase, it's the equilibrium tide, but in the main sequence, there's regions where you need to take into account the dynamical tide. I didn't only compute this for one solar mass model, I did it for a bunch of models, for instance, for a 4 solar mass model as well, where it's not only the stellar evolution that changes, your radius evolution that will change, but also the equilibrium tide will change and the dynamical tide will change. But if you're interested to learn all the tiny details about how this changes and why this all changes, I encourage you to read my paper on exactly this, the tidal dissipation in evolved low and intermediate mass stars. But for now, I just want you to remember that we can compute tides ab initio from first principles from stellar evolution. So then I can go on and think about the other part, which is mass loss. Mass loss will change the orbit as well. And let me jump straight into the equations. When you want to see how the semi-major axis changes, you have this long equation, which is proportional to, first of all, the mass loss of the AGB star and the mass of the AGB star. And then you have other properties like Q, beta, and eta. Q, the mass fraction. Beta will be the mass accretion efficiency. From all the mass that is lost, how much material goes to the companion and is accreted by the companion. And then you have eta, which is a term for how much angular momentum is lost because of the loss of material, but also the interaction with the wind. And these properties you can compute analytically if you do a big assumption, which is that the mass loss or the wind doesn't or barely interacts with the companion. When you do this, you get a beta, which we call beta BHL, Bandy-Hoyle-Littleton, given by the equation here, and an isotropic eta given by the equation here. But this is a quite strong assumption. How do we know if the wind will strongly interact or not? Well, yes. Looking at observations, that's actually what you see behind. You see a lot of structure, so we expect that the companion has a big influence. But what we can also do is simulate this. And to do this, we need to understand how stellar winds work for AGB stars. How does it work? Well, we have a diagram here that shows this. On the left, you have the AGB star itself, where there's a lot of convection going on in the envelope. And due to this convection, you have pulsations. These pulsations will push material into the red region, where it's cool enough for molecules to condensate into dust. These dust particles are quite opaque and will be pushed away by radiation pressure. So they will be caught by radiation pressure and move outwards. By moving outwards, they collide with the remaining gas particles, also dragging these outwards. This creates a steady outflow of material where a lot of chemistry, a lot of complex chemical processes can take place. Now, how do we simulate this? We can go through smoothed particle hydrodynamics, SPH in short, which means that we solve the fluid equations on individual discrete particles and follow the particles to follow the fluid. When we have these particles in the simulation, we need to account for additional forces in a simulation, which is the gravity of the AGB star itself, as well as the gravity of the companion, but also the wind, which we condense into the wind launching parameter. And one assumption that a lot of people make, and I will make in the start here as well, is the free wind assumption, which means that we take gamma and we put it equal to 1, meaning that we completely cancel out the gravity of the AGB star, meaning that if we have material that flows away, we won't catch it back from gravity, we'll just let it go and let the companion influence the wind. When we do this, we have to start from material. So what we do is we take the shell or the sphere at the radius of the AGB star, we launch particles from there, and we launch particles from there we let them just go, and we take a companion and let it orbit around. And when you do this, you get simulations that look like this. I'm just gonna let it hypnotize you for a while. So what do we actually see here? You have the AGB star on the left now and the companion orbiting around it. And you can see clear spiral structures tailing behind it. And this is because exactly of strong interaction with the wind. So it's not a weak interaction. And if I zoom in on the companion, you get something that looks like this. You can see that there's a disk forming around the companion, an accretion disk. So yet another sign of strong interactions. So for a next step, I have to give credit for a PhD student in the Netherlands, Marta Saladino, who in 2018 and 2019 did 3 beautiful papers exactly on this topic. She did such simulations with a different code, but with the same setup as we used here. And she computed beta and eta for a grid of models. And here on the images, you see beta and eta, and on the x-axis is the terminal velocity, the velocity the wind has when it's just expanding outwards, divided by the orbital velocity. The dashed lines is the Bondy-Littleton in this case and the isotropic case here. So the equations I showed before. And you can see that the simulations deviate from that. So for beta, you see an increase, although it looks small, the plot here is logarithmic, so it can be a big increase in accretion efficiency. And for the angular momentum, also an increase is seen. Here it's a bit better visible. And what she did is she came up with different equations and then fitted some parameters to get these equations as close as possible to her simulations. So we have equations we can now try to plug in to our stellar evolution, or orbital evolution. But before we do that, this free wind assumption is quite a strong assumption, taking gamma equal to 1, neglecting all this complex physics that goes into launching the wind for an AGB star. So what we in our group try to do is to include more of the physics going on, where I picked one of the boxes, and I looked into a bit dust condensation, but mainly the wind acceleration. So I went back to this equation and I said, I don't want to take gamma equal to 1, I want to actually compute it. So what we can do is compute the Eddington factor, so it's the radiation pressure divided by the gravitation, or the radiation acceleration divided by the gravitational acceleration, for which we need an opacity. And I said a bit of dust condensation, because for dust I just took a profile dependent on the radiative equilibrium temperature. So if you have a radiative equilibrium temperature that is cool, dust has condensated. If it's high, dust will not it's not condensated, and you don't have a lot of opacity. But to do this computation, you still need this radiative equilibrium temperature, and you also need the flux that gets to the material. To know this, or to compute this, I took the radiative, from the radiative transfer, 3D radiative transfer code Magritte that's been developed here at KU Leuven. I took the ray tracer and I adopted it to work as efficiently as possible with the SPH formalism, such that I could have a good grasp on these two properties in a computationally fast way. And I looked at some assumptions we can make in the computation, and I came up with 4 different approximations, where the free wind is still what we had before, gamma equal to 1. The geometrical approximation is just what radiation would you have if there's no material, no absorption, no emission. And then you have the attenuation and the Lucy approximation, which both take into account some of the absorption and some of the re-emission of the light from the dust, or due to the dust. And when you try to see, well, what of these models is actually closest to the radiation pressure you would compute if you would do full 3D radiative transfer, turns out this is the way in terms of accuracy. So free wind is the least accurate, and the Lucy approximation was the most accurate. So if you start from the free wind, the models we used in equations before, well, you can see that the morphology and the wind interaction is different. So it could be important to take these effects into account when computing the orbital evolution. But for now, there's still a lot of other physics we need to, if you're interested more into how the algorithm actually works and how this interaction from radiation and the wind works, I encourage you to look at my other paper exactly on this topic. Before taking these models and computing again beta and eta, there's still a lot of other physics we need to include, and for that I have other people here in the room. Owen, for instance, is working on pulsations, which are crucial to get the self-consistent launching, because at the moment we just launch at a specific velocity, but pulsations are more self-consistent. And Camille is also working on chemistry, on how to include chemistry in our simulations in a fast way, such that we can have feedback from that as well. For this, we also need the photo dissociation, which is something Owen has worked on as well. So with our team, we try to make a better model, and if it's done, we can try to recompute these beta and eta values. But before we can do this, we can just work with the beta and eta values that Marta gave us, and we can go on. So if we have this beta and eta, we have a way to calculate how mass loss will influence the orbit. So we have tides, which we discussed, mass loss we discussed, so we can try to compute the orbital evolution itself. And let me give you an example. This is an example. I just plugged in some numbers. You have a 1.5 solar mass model with a 1.15 solar mass companion and an orbital distance of 7 AU. And when you compute the orbital evolution, you can see that when mass is lost in the RGB phase, the semi-major axis increases a little bit, so tides are less strong than mass loss, and mass loss will increase the orbit, and a little bit of the mass is accreted by the companion. And in the AGB phase, a lot happens, so let me just zoom in on that. Throughout the AGB phase, when mass starts to be lost, you see that the semi-major axis decreases and doesn't increase. And why does this happen? Well, this is exactly because of the equations from Marta. More angular momentum is lost because of the strong wind interactions, and therefore it's not increasing, it's decreasing, because you lose this angular momentum from the orbit. And at first it just decreases slowly, but at some point tidal dissipation will take over, and this is a fast, or when you're closer to the star, tides become stronger as well. So this is a rapid evolution, and the star will plunge into the AGB star. And at this point, I give it to the common envelope people. I'm not able to compute further evolution with this model, but I know what properties to give to the common envelope people. And before the common envelope starts, you can also see that mass accretion goes faster and faster and faster because you're closer, so more material is caught by the companion as well. Now, a different example, maybe a little bit more close to home, the death of the sun. If we look at the inner solar system planets, what will happen if the sun evolves? So let me just already evolve throughout the rest of the main sequence for the sun. Not a lot happens. But if you zoom in for the evolved phases, you have the RGB and the AGB. First, in the RGB, what happens? Venus, Earth, and Mars move outwards, so the three of them still remain, but Mercury merged. So Mercury is lost from the solar system. Moving forward to the AGB phase, now Venus plunges into the star as well, but luckily Earth and Mars still survive. Going further, it's a stable evolution, so what I predict is that we're left at the end with 2 planets less, but Earth has survived. If the habitability survives as well, that's a different question, but the body at least survives. Now these computations I implemented in Python for the moment, so they're at the moment not extremely computationally fast. So if we want to do population studies with this model, I need to speed up the code. And to try to do that, I will look at the code Spheroid. This is a code that had become open source since January, so it's quite young code. Stands for Star-Planet Interaction, Rotational and Orbital Integrator for Dynamics. It's been developed in Paris in collaboration with Geneva, and it's recently been translated to Rust. So it's quite fast, and it already takes into account some of the tidal effects, but it's mainly focused on the main sequence and the pre-main sequence, so I will evolve it or upgrade it for the evolved phases and implement my methods for mass loss as well. So that already brings me to my conclusions. Maybe a bit fast, but more time for questions. So both stellar tides and mass loss are crucial if you want to calculate the orbital evolution, in this case for AGB binary systems. It's important to take both effects into account as accurately as possible. And looking at our Earth, it will luckily survive the violent AGB phase of the sun. And in terms of future work, we need to further work and further develop this AGB wind model to get as close to the eta and beta values that are actually happening in the systems out there. We need to, or I need to speed up the code and go to spheroid, I will go to spheroid to do that. And when this is done, I can perform a population study to see how the population of companions around main sequence stars will evolve to companions around white dwarfs. Thank you for listening, and glad to answer some questions.
Thanks much for the interesting talk and a very solid statement that the Earth is going to survive. That's a good news. Time for questions. Oh, there's a lot of questions. Well, thank you for reserving enough time for questions.
Hi, Matt. Thanks for the talk. Could you also just elaborate a bit on the, for the tidal effects, so the first part of your talk, the effect of eccentricity, like when you go from non-circular to...
So what effects it would have, or what?
Yeah, because I think the equations at least you showed was assuming circular, right?
Yeah.
So yeah, just...
In terms of, okay, so there's some things to add. If my pointer keeps on working, the videos are a bit large in size, so PowerPoint crashes a little bit. So for the equation, if you have eccentricity, it's tidal dissipation you compute on spherical harmonics, and circular case is quite easy because you have only one spherical harmonic to care about, but when eccentricity is introduced, you need to care about more spherical harmonics. So your equation here at the moment only contains one kappa value, one imaginary part of the love number, but this becomes a series of love numbers. So when you go to higher eccentricities, you need to take into account more terms. But the equations here remain the same, except for the tidal frequency. So your tidal frequency for each harmonic series will change. So if you have an orbital period, let's say of a year somewhere here, and it's eccentric, then you have a value here, plus a value there, plus a value there, plus a value there. So you get more terms to take into account. But you can do this. You can write it down and take them into account. Was that your question, or?
Yeah.
Okay.
All right, thank you for that really nice talk. You mentioned at some point that you see a lot of structure in these post-AGB outflows, and that tells you the influence of the binary on the evolution of the structure. Do we have enough observations of post-AGBs to have a population of things that were and were not influenced by binaries to really see those structural differences and to get a better sense of how much impact it's having?
So you are referring to this image?
This image here, yeah.
So this is from an AGB star, so it's not a post-AGB star.
Sorry,
But,
AGB or post-AGB, but the structure you said came from the effect of a binary.
Yes.
Do we have enough observations of AGBs to say these are the binary ones, these are the non-binary ones, and this is the influence? Do we have a more spherical outflow from single AGBs?
We have a few of those observations, and to my knowledge, they all have complex structures, and we expect all, or at least most of them, to have companions. So having a spherical outflow, we don't see a lot. We mainly see complex structures.
Why do we expect most of them to have companions?
There is a bit of doubt about that. So looking at statistics, we expect half of them to have companions in the main sequence, up to 99 to 100% if you include planets. But if planets can induce these structures, is not necessarily certain. We do simulations for them and they have structures but not necessarily strong enough. And yeah, we're not entirely sure why we only see the binaries. There's other theories put forward as well in terms of rotation, in terms of magnetism, but they don't. Doing simulations for them doesn't work really well to get to the structures we see.
Cool. Thank you.
Maybe to quickly follow up on this, Mats, does the companion have to be of the stellar mass, or like a brown dwarf or a planet would also result in such a structure?
I know Silke did simulations for planets, and you still see structural differences. If it's strong enough to observe, I don't know, but there is differences, or there is perturbations and changes. But in our simulations, as I said, we don't do pulsations, so pulsations could also induce already some structure. So the combination of a planetary companion and pulsations, maybe yes, that would be visible, but I can't really assess that. Other than that, there's been speculation for the long secondary periods. So for evolved stars, you have a primary pulsation coming from the pulsations of the actual convective envelope, but sometimes we see a secondary pulsational period that's not always clear where it comes from. And people have put forward that this comes from companions, and these companions could be brown dwarf mass.
Thank you for the interesting talk. I had a question about tides. So you mentioned, I think, on slide 17, yeah, so that's this line, this critical period. If you go below that, you have issues with modes. So I was just wondering, is that something, if you would use, for example, gyre tides, does that contain, let's say, all the necessary information to solve that problem, or is there something else going on here?
So your question is, could you use gyre tides to improve on the lower part?
Yes.
Yes. I'm not extremely familiar with gyre tides, but I know that the waves could also be broken by non-linear effects, and I don't know how that's included and if that's included in gyre tides. But in terms of the pulsation modes, yes, this can be done by gyre tides.
Yeah, I think the nonlinear effect is not included, but yeah. So,
yeah.
Okay, thank you.
Thanks for the nice talk. You showed some plots that were the evolution leading up to common envelope, right? That's where you kind of stop.
Yes.
And then observationally, we have a lot of these post-common envelope systems. So using those systems, can you, like, are there any imprints of the pre-common envelope evolution expected in post-common envelope observation? So can we say something about all this based on observations that I think one of the plots you showed this nice distribution from Hans, and we have different kinds of post-common envelope binaries. Some are stripped, some are I think on the RGB phase, some are on the AGB phase. Can we differentiate between them? Are there any imprints left after common envelope evolution of what happens before?
I'm going to say probably, but I'm not a common envelope expert. But I'm sure if we talk to them together, they would give us an answer. But I'm not sure myself.
Okay. Thanks.
Hi, thanks for the great talk. I have two small questions first. Was the wind model you're assuming on AGB? Like you have computed this main model from MESA, right?
So, sorry, could you repeat?
What was the AGB wind scheme you're using? Or wind scheme on AGB?
Reimer's scheme.
Reimer's, right. And what's the value of metallicity or solar metallicity that you have assumed?
It's solar, so.
Yeah, solar, but there are a few solar metallicity.
I think it's the, I'm going to say Asplund, but I'm not.
So that will be 0.014, right?
I think so.
Okay. So I'm not that familiar with AGB winds, but because it seems like the you are looking into the details of this AGB wind, and even small things there can impact your results. Yeah. Do you think things like your results will change if you assume, for example, because even for AGB wind model, like Reimers, like sometimes people use blocker wind. I was actually trying to quickly look up what wind schemes are available for AGB stars in MESA. But do you think your results will change if you use, for example, a different wind scheme or a different solar metallicity, especially like the composition? So,
for the composition, I'm not entirely sure because I haven't played around with that. For mass loss, yes. I'm also going to say a lot. And it's mainly because if you have less strong winds, then your AGB phase will take longer. So tidal effects have longer to act. So if you look at this plot, if the AGB phase, if you reduce, so what I did is I reduced the mass loss by a factor 10. So it sounds like quite a lot, but it's still within the big uncertainty we have for the mass loss. We don't really have a good grasp on what the actual mass loss will be. Then Earth will be almost swallowed. And it looks quite far, but it's just tides have 10 times more time to act, so they have a stronger effect and will influence more. So for the metallicity, I'm not sure I can answer, but for the mass loss, it is important, and it's something we need to look into as well.
So we still can't say for 100% that Earth will survive.
Sadly, I cannot say it for 100%, but if we assume this model, I can.
Thank you.
Thanks, Mats. That was a really great talk. I just wanted to clarify something about one of your assumptions. Could you go to the external acceleration slide?
Yes.
I just want to see if I'm over-interpreting it. So you say that you cross out the term from the donor star, right? The mass-losing star, if I remember this correctly. So, and that's the influences. Okay, so that's on the wind particles, yes? So does this mean that the particles do not experience a Roche geometry in terms of the gravitational potential, or is this purely in terms of the wind acceleration? So for example, I'm asking this in the lens of wind funneling effects through Roche geometry. So is this natively accounted for in the system, or by crossing out this term, are they only experiencing the gravity of the companion once they've been lost from the star?
That's one of the big reasons we want to improve upon the model. Because indeed, they don't experience the Roche potential. And it's expected to have a big effect if your Roche limit and your dust condensation, or if your dust condensation radius is outside this Roche limit, you expect a lot of tunneling indeed, which is not in any way included in the models yet.
Okay.
So this will influence the beta by a lot. So that's one of the big reasons.
Okay, because it would be really nice to self-consistently do this. In the past, people have tried to write down analytic approximations, but I mean, the setup is perfect for testing it. I gather it's quite challenging, though, to add in this additional physics, because it's an additional gravity term on every particle. So.
Well, the gravity term itself is not necessarily that complicated, but getting the right radiation pressure, getting the right pulsations, implementing the pulsations in the correct way, having the right resolution to still be sure that it's consistent and it's not just resolution effects you see, takes a lot of computation time.
Okay, so in principle it wouldn't be that challenging to add back in this additional gravity term and see just on the current physical setup how much of an influence that Roche funneling has?
The thing is, if you include it and you neglect gamma, then your material just falls back, because you start with or velocities below the escape velocity. So in that way we need the actual radiation term, which is then difficult to compute, so we take it to 1 to make it easy to compute.
Okay, thanks very much.
Hi, Mats. Thanks for a great talk. You might already predict what I'm going to ask you, but if you have to do with tidal waves, then the internal rotation of the star is just critical because it completely dominates the way the waves behave. And this plays at two fronts in the equilibrium models, so in your MESA models in your case, but also in the predictions of the tidal dissipation. I think you didn't include rotation, am I right? Yeah.
Not at all.
So, yeah, well, that's a big caveat. Do you plan to, or is that too big of an effort?
I'm going to say for the equilibrium tides, I think it's fine without, especially when the star is a big AGB star, because we expect them to be quite slow rotators. But indeed, for the gravity waves for the core, it can be a bigger effect. And something it's difficult to assess the rotation in these two regions, because it will have or if you have tidal spin up, then it will change. So I decided to neglect it for everything, because it's more consistent than trying to have it, but then not entirely having it correct. But with the spheroid code, I'm not going to go to the slide. For the spheroid code, that's they do include a two-shell structure or two-layer structure with the core and the envelope, so that I can trace both rotations. So then I might hope to have a better grasp on what rotation is, and if possible, I will try to include it. But it's a problem I will look at later.
You may as well give you our observed rotational profiles, right? So I'm mainly talking main sequence here, where this effect is big, and we have like thousands of stars by now with internal rotation measurements.
For main sequence, indeed, true. I was talking about mainly the giant phases, but in the main sequence, completely right.
Yeah.
Hi, Mats. Thanks for the very broad overview as well in the talk. For the opacity calculation, you have dependency on equilibrium temperature, but would you expect also relatively like significant dependency on the condensation temperature? I guess you have to assume now based on whatever composition you have assumed, so it's a fixed value.
Yes.
But then perhaps if you also connect to Poojan's question a little bit on the composition, if you have like a different metallicity or something, would you expect a strong compared to maybe it's a small change and then it's
probably it will change. I'm not entirely sure how that would directly relate. What I can say as well is that your composition already changes throughout the AGB phase itself. You go, or your carbon to oxygen ratio changes throughout the phase, and this gives you a carbon-rich environment and an oxygen-rich environment, and it's a transition. And you see that dust indeed nucleates differently for both regimes. So throughout the evolution, you would need to change the condensation temperature, which is something I don't know how. And metallicity will probably change this as well. But for that, there's other people to talk to who do dust nucleation who will have a better answer than me.
Yeah, and then I have another question on the accretion by the companion. So do you know from your models what is the spatial extent of this accretion disk? These companions are...
Yes. So when you have the spatial extent, you mean how big the disk is?
Yes.
Yeah. So
I see that. It's a few AU or something.
Yes.
So is the surface density sufficient, you think, to form second generation planets here?
If you look at the mass, the total mass of the disk is a few moon masses. So planets
only a few moon masses.
Yeah,
okay.
yeah.
Okay.
So it's
not probably sufficient for that.
Yeah.
Okay. But maybe in certain scenarios, you expect. Is this really your nominal case? Like, if you draw a Gaussian, this case would lie in the middle, or it could be.
I'm not sure.
Okay.
Because the mass of the disk also depends on how. The disk is quite hot. It depends on how much you can cool the disk to keep the material, which is also one of the approximations that goes in there. We don't do all the cooling that we need to. So I'm not entirely sure.
Yeah, this is just out of curiosity.
Yeah.
Okay.
I'm not sure. Sorry.
Yeah. Thanks.
Thanks for this very interesting talk. So I have a question about a very fundamental assumption in your calculations, and that is of hydrostatic equilibrium. So you assume that these AGB stars are in hydrostatic equilibrium, but I actually wonder if they are in these phases where they experience these pulsations. Could you comment on that and how you'd like to handle it if they're not in hydrostatic equilibrium?
Where exactly do you mean in the?
Yeah, so what I mean is that they may be dynamically unstable in these phases where they have these ejections, because the radiation pressure will basically exceed the gravitational force. That's kind of what you show as these outflows. So that also means that, you know, for a MESA model, for example, to compute a model from one type step to the other, you assume that the star is in hydrostatic equilibrium. But I believe maybe this is actually not possible in this case, because they have these outflows. So, yeah, so I wonder if this also plays a role in how this shapes these nebula around these stars.
I'm thinking about, yeah, I'm not really sure how that would change your model. It'll probably change your internal structure a little bit if you include this, which then might have an effect on the tides.
Yeah, I'm thinking it might actually even enhance the pulsations, actually. That you start to be radially unstable and have even like larger amplitude pulsations. And this is something you can actually explore in MESA in this hydrodynamical mode. So I'm just speculating that this might be something interesting in this phase that you're looking at
so you
specifically.
You mean enhanced mass loss due to this?
Yes, exactly. Yeah, just wondering if this is something you had considered before.
No, I've not,
or not
really considered it.
Yeah.
Yeah, the mass loss prescriptions we used are based on observations.
Mm-hmm.
So I guess if we would enhance the mass loss, then it would maybe track the observations less, because it's a bit of both ways. So I'm not sure. It could enhance the mass loss, but then we need to readjust the formulas to still have the same mass loss compared to what we observe.
Yeah, so I think this is actually a natural evolution of the star. So it will. So at the end of the AGB phase, where it goes to this this post-AGB phase, where this mechanism might play a role. So yeah, maybe we can chat about this at some point.
Would be interesting.
I look at this in the context of red supergiants. So this is completely different. Well, maybe quite different masses, but I think the physics might be quite similar. So I find this quite exciting. Yeah.
Would be nice to have a chat.
Yeah.
Thanks for the nice talk. I have a question, because you showed two examples. One is in a 7AU binary which merges,
yes,
and a planet survives.
Yes.
Planet Earth survives. So what is the main physical mechanism to explain this difference?
It's mainly the angular momentum that is lost from the interaction of the wind and the companion. So the material around the companion that creates these spiral shapes and will reduce angular momentum from the orbit. And this works efficiently if your companion is massive. So the mass of the companion is a crucial component there. And this mechanism will then reduce instead of increase the semi-major axis because of the mass loss. And for planets, you reduce, or your angular momentum is. So for planets, you take away less angular momentum and increase, while tides decrease it, but the increase is stronger. While for more massive, the angular momentum from the winds is more efficient, or the angular momentum loss from the winds is more efficient. So you decrease because of this and decrease because of tides, so you get the common envelope.
Okay, interesting, because in the post-AGB stars, we see a lot of stars that survived with the quite wide orbits, wider than we would expect, and do not merge. So it's a bit a contradiction, but
yeah,
something work to do.
Something I have to look at as well is again related to Connie's question, rotation. So at the moment in my orbital evolutionary model, I don't take into account rotation as well. So the spin-up from the tides is also not included, but with the spheroid code, this would be automatic because they have already included it as well. So when I go to this code, I can include this effect, and maybe tides are less efficient, or tides will be less efficient then, but how less efficient, I don't know yet. So this could also bring it closer to what you say.
All right, there is still maybe time for one very quick question. A very quick one, okay.
Hi Mats, thank you for the talk. I wonder if there is a scenario that would result in a fully ejection of the companion of the system, so that the companion really becomes gravitationally unbound. That was quick, huh?
Not with equations I use. Maybe very, very, very exotic if you have the thermal pulses. So in the when you have a pulse here, your mass loss is larger as well at this point. So maybe if you're at the verge or you don't have a lot of angular momentum and then you have this sudden burst, it's like when you have supernova explosions, you can also have ejections from that. So maybe there's something could look similar, but not in the formalism I use. Everything will always be bound.
All right, so we are at the hour. Let's thank Mats again. And thanks everyone for the impressive activity in the discussion session, and see you next week.